So thank you, and happy birthday, Charlie. Everybody else was saying it at the end. It's an honor to be here. Okay, so I'm going to talk today about orthogonal matchings, and this is joint work with actually an undergraduate student, Sophia Putt. And it's always nice when you get an undergraduate student who gets it. I'm really happy she's gone on to do a master's, so hopefully university near you. Okay, I'm just going to start with some notation. This is I did lexicograph for the product. I know it looks like there's a lot there, but this is all stuff you know. You take a graph G, and you kind of blow it up, and you put something in the blow up. Usually the thing in design theory that you want to put in the blow up is nothing, right? You just want to blow it up, and you have that empty, and eventually you're going to fill that up with something. And so I just want to sort of push this notation, because everybody's always trying to figure out, how do we write this down? And actually, this notation, G blown up by H, if we're actually going to put an H in, or more specifically, if we're not going to put anything in there, we're just going to blow it up and leave it empty, G blown up by W. This is a notation I've been using, and so I find it's really good. And it's the great thing about it is that everybody always is trying to figure out how to do the multipartite graph with n parts of size W, and it's really easy with this notation. The other sort of things that you need to know is a matching I'm going to call M sub k. So this is a matching that has k edges in it, 2k vertices. And just sort of notice that if I take a matching of size 1, an edge, and I just blow it up by W, that's the same as taking k2, which is the same thing, and that's just the bipartite graph W. The next idea that we have is a sort of general idea of graph decomposition. So we give it a big graph, H, and we want to decompose that big graph into edge disjoint copies of little graphs that are contained in our collection G. So we give it a collection G to start with. And usually we restrict ourselves, G really just has one element in it. And so the classic example, of course, is a Steiner triple system. Right? So here the big graph is Kn. We're trying to decompose Kn into triples. And the triple can be, depending on your flavor of the day, it could either be a complete graph with 3 points or a cycle of 3 points, same thing. This is a sort of classic example. And Patrick talked a little bit about the history here, but I just want to point out that Kirkman in 1847 proved that a Steiner triple system exists if and only if V is 1 and 3 1 6. Steiner, 6 years later, posed the problem. It was then, 12 years after, solved again by Rees, and of course it's named after Steiner. I actually looked at Steiner's original paper recently, just for various reasons. And it's interesting, he actually poses a slightly different problem, and this is just a throwaway problem at the very end, very short paper, but it's in German, so it's right. Okay, so here's a Steiner triple system of order 9, 9 points, 12 blocks, and of course I've colored them. The reason I've colored them is because I want to talk about resolution classes. So, and Patrick mentioned this in his talk too, a parallel class of a design is a set of blocks that exactly partitions the weight set. So there we go, there's parallel class 23, 4, 5, 6, 7, 8, 9. And here's another one in blue, 1, 4, 7, 2, 5, 8, 3, 6, 9. And of course, in this particular case, we can partition the block set into parallel classes, which are the 4 ones there, 4 color classes, and that gives us a resolvable design. And this is a classic example of resolvable design, so the Kirkman triple system. So just in contrast, Kirkman in 1847 posed the problem, does there exist a Kirkman triple system with LP? And the obvious necessary condition is that V is 3, not 6. Ray Shahuri and Rick Wilson, who is here, is in 1972 proved that this was true. That indeed, they exist for every value 3 and 6. And that was 120 years, as opposed to the non-resolvable case, which was solved 6 years before it was proposed. So I just want to get across that making things resolvable is in some sense a lot harder. Kirkman actually died without knowing whether a KTS-21 existed or not. Now that's a bit of a kludge, because that turned out to be a very hard case. It was one of the later ones to be found in some sense, later 1970s. Okay. So you can recast the language of all of this into the notion of a factorization. So a resolution class is just a factor, and a factorization is just a resolvable result. So, and in particular, of course, very common to talk about D factors, or D factors, a spanning subgraph where every vertex has degree D. In particular, we've got 1 factors and 2 factors, which are the main things that are sort of interest here. 3 factors are way too difficult. So 1 factor, or 1 factorization, is a perfect matching. So here's a 1 factor, which we saw some of this morning. Basically, each row there is a resolution of all the points, so 0, 1, 2, 3, 4, 5, 6, and infinity, and there are always n-1s for the classes. It's well known that 1 factor exists if and only if n is even, factorization of kn exists if and only if n is even, and similarly, knn can be done for all n, and it's pretty easy to see how that's done. Now, Patrick mentioned this in his talk. This is sort of the more recent idea, is one of orthogonal resolutions. So a resolution is just a partition of block sets into resolution classes. But you can have 2 different partitions that are different on the same fundamental block set. And if the resolutions in one class and the resolutions in the other class intersect in at most one block, that's called an orthogonal resolution. And these are things that have been studied for some time. They're sometimes called doubly resolvable, orthogonal resolution. Now, the way to think about these things is not the slide that I just showed you. They can be thought of as, notice I did this, right? It's square. You've got one resolution class this way, another resolution class this way, and you look at it as a square. So this is a square array. This is an orthogonally square. And these have been studied. That actually goes all the way back to Kirkman in 1847. I think it might actually be his 1853 paper, where he presents that blue square that I just showed you, but not quite in that form. They were studied by Roon in the 50s, hence the name. And then finally, Mullen and Wallace in 1975 proved that they exist if and only if n is even. That's obvious, because you've got to have a 1 factorization. And n is not 4 or 6. So you can't do a root square side 4, and you can't do a root square side 6. So you can sort of think about this. I sort of, at the beginning, talked about C3 decompositions. Whether it's Kirkman systems or Steiner systems, depending on resolvability. And you can ask, well, can I take a Steiner triple system and doubly resolve it? And these are known as Kirkman squares. The square has a side of like n minus 1 over 2. Mathen and Vanstone in 1980 showed that you can't do it for n equal 9 and 15. 9 is easy to see, doesn't take very long. 15 is a little bit of work. And here's the connection of this to Charlie's work. Charlie, together with Esther and Alan Mills, showed that they exist. These Kirkman squares exist with 23 possible exceptions. Now, 11 of those exceptions were solved subsequently. So, as far as I know, this is the list of the 12 possible remaining exceptions. And there's an interesting thing here. We know that 9 and 15 don't exist. The smallest unknown value is 21, but after 21, it jumps to 141. So there's a real question, and Patrick mentioned this in his talk, about whether this doubly resolvable KTS21 exists or not. And it's very hard to know at this point. So what this means, of course, is that this is exactly the same picture that Patrick had in his talk, because this is the smallest example. And it comes from one of Charlie's papers. And it's the smallest example of Kirkman square for the 27. Because we know the 9 and the 15 don't exist, and 21 is still unknown. Okay? And everybody would very much like to know, does the 21 exist or not? So you can also, instead of using Kn, you can, basically, we want to be able to do the case when n is even and 0.16. And it's very standard to just take out a one factor, and then we can look at the 0.16 case. And these are called doubly resolvable nearly frequent triple systems. So they've got a great acronym, DRINKS. And again, Charlie, together with some other people, showed that they exist with 64 possible exceptions, which I list here. And here is the smallest known example, because it's known that the 6 and the 12 don't exist. And I don't know why I put it in my letters. And that's the smallest known example of DRINKS of 18. Okay. So another variation that's been looked at by myself, Andrea, Brett, and Eric Mendelson is the idea of just sort of looking at an STS not as a K3, but as a C3. So the general idea is you want to take a cycle system that is doubly resolvable. So the first thing that you think of is, well, what about Hamilton cycles? And that's really easy, because you just take a Hamilton cycle and you just, Hamilton decomposition, sorry, and you just put it down diagonal and you're done. Right? Doubly resolvable, but it kind of doesn't feel like you've really done it. We did show that an OCD, orthogonally resolvable cycle decomposition, exists when K is 4, so 4 cycle decompositions. Interestingly enough, we have these non-existence results again. You can't do it when n is 8, and you can't do it when n is 12, but everything bigger than that. And it sort of seems to be, one of the things that's very common with these types of problems. You can do it as long as n's big enough, but there are these non-existence results for small values of n. We looked at 6 cycles as well, and showed that if n is congruent to 6 mod 12 and big enough, 12 possible exceptions, you can do it. But the case where n is 0 mod 12 is still open, right? Theoretically it's possible. We also gave some recursive constructions, which I'll talk about, and looked at some the cases sort of MK, so you've got a K cycle into an MK graph for small values of n. So say a few words about that. So the first one is 2KK, so you want to do a K cycle into something twice the size. They don't exist for K, so this is your cycle size, 3, 4, 5, 6, or 7. But 8, it does. The 16-8 exists. And in general, we showed when K is 0 mod 4, then you can do it. But when K is 0 mod 4, still wide open. Similarly, if m is 3, so now we're taking a k cycle, we want to put it into 3k, we showed that this works if k is 0 mod 3 and big enough, bigger than 9. We could do it, but the question when k is not 0 mod 3 is still wide open. Right, so I came here to talk about orthogonal matchings, which I haven't mentioned at all. So, orthogonal matchings. The idea is to generalize the notion of a room square. Instead of just having orthogonal one factors in each cell, instead of putting just a single factor, we're allowed to put a matching of any size that we like. Okay? So, and I use this notation OMD and K, so this means we're going to have a matching with K edges, and we've got n points in total. Of course, as I said, we really want to look at the squares. We don't want to look at the notional way of looking at it. So here's a square. So in this case, we've got 8 points again, and each matching is a 2 matching. So we've got a pair of edges in each cell. So here we've got 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that's a resolution class. And here we've got 0, 1, 2, 3, 4, 5, 6, 7. So a resolution class, and that's true for each row and each column. And so it has this property for So obvious necessary conditions, the number of rows and columns is the number of times that a point appears in the factorization, and that's n. So this example on 8, we've got 7 rows and 7 columns. Each row and column must divide n into matchings, each of which is on 2k points, so obviously we're going to have n congruent to 0, 1, 2k, otherwise we won't be able to do that. So we were able to show that an orthogonal matching design, nk, exists if and only if n is congruent, the necessary sufficient conditions are sufficient, n is congruent to 0 mod 2k, except for the 2 known exceptions, the room square. Those room squares are exactly the case k equal 1, and a room square where n is 4 or 6. So only 2 possible exceptions. And for the rest of the talk, I'm just going to give you a sort of idea of how we did that. So the first thing to notice is k equal 1, as I just said, are room squares, so that's we don't have to worry about that. I just want to talk about the notion, so a few notions that we need. The first one is the notion of a transversal. So a transversal is exactly what you would expect if you do transversals. We have each row and each column has a transversal, and every point is in the transversal exactly once. So exactly what you would expect. Just one thing that's a little bit different is that transversals can have empty cells in them. And so in general, we can have empty cells. For the room square, for example, where we have exactly n non-empty cells. So here we have at least 8, exactly 5 cells. So, idea of transversal. The other idea is the idea of a hole. So here's this example again. It's interesting when that happens. We can define the idea of a hole. A hole is just a square array of cells which has nothing in it. Okay, so some special cases that we can do. So an OMD M1K. So this is a matching blown up by K. Well, just think about that for a second. I've got a matching, a single edge. I blow it up by K. That's KKK. That's the complete multi-project graph. So just another way of saying that. And we know that there's a one factorization of that. Here it is. Here's an example. We can color it. And then, because the size of the array of the matching is exactly what we want, so each matching in the case k equal 4 has exactly 4 edges in it, I can just do my diagonal trick. Right? Remember when we had the Hamiltonian case? Just put it down the diagonal, and there you go. So that's a really easy case, actually. And, you know, it has a transversal, it has a we can also do the case where 2k. So what does this mean? This means we've got exactly twice as many points as we have the size of the matching. So here's an example with k equal 4. So what do I want? Well, I want a 1 factorization of k8, but that 1 factorization is going to have 7 1 factors, and each of them is going to have 4 edges. So again, I just put it down the diagonal, and I'm done. Nice thing to note about this, if I look at the back diagonal, that's exactly a transversal. And if I sort of take this little piece up in the corner, that's a hole. So, and this will be useful later on, I can say that we have a transversal and a hole the size k as well. I can also do the case 4k. So just to sort of give an idea, take your point set x, divide it into 2 pieces, divide those into 2 pieces, and now we can sort of cross-match them in different ways. So we can take, this is kk, this is kk. It's the complete bipartite graph on k vertices. This is the same, this is the same, this is the same. So what we can do is we can take the decomposition we had of kk's, complete bipartite graph of k vertices, and kind of put them together. Because what did they do? They just went down the diagonal. Right? That's how they did it. So I can just put the other one down the other diagonal. So this is the sort of blue one. I've put the k's and these together. And these can go together because they're on disjoint point set. And these two can go together because they're on disjoint point sets. There's one, and there's the other one. I call this one A, and I call that one B. That's the blue one and the red one. And then I have another matrix C, and what's this? Well, this is just a decomposition of these 2 sets. And again, they're on a disjoint point set. How did I do that? Well, I just put stuff down the diagonal so I can stream on the diagonal. And so that's a decomposition of A0 of A, and that's a decomposition of B. And I put this together in a sort of block form matrix, and I get something that's exactly like this. And the example on 8 that I gave earlier exactly was created by this method. I can also do 6kk. So here's a k222. Solve that case. Blow it up by k. So each of these now is a matching blown up by k. We know how to do each of those cells. Right, so on each of these, we put one of these OND M1Ks, like bipartite graph on each of those, and this, and then the resulting graph is exactly what we want. So I don't want to go into too much detail, but I think how much time do we have?
You're about out.
Okay, yeah.